Most people think of bad weather as something that moves. A storm rolls in, it does its damage, and then it leaves. The sky's clear. The temperature drops back to normal. Life resumes. That is how weather has always worked in the mental model most of us carry. Dynamic, temporary, always in motion. But there's a weather pattern that breaks that model completely. A pattern where the atmosphere essentially seizes up, where the systems that normally push weather from one place to the next grind to a halt, where a single weather condition, a brutal heat wave, a relentless drought, a week of nonstop rain, parks itself over a region and simply refuses to leave. Not for a few extra days, not for a week. For weeks, sometimes for months. The people living under it watch the forecast and see the same conditions repeating day after day after day. The same temperatures, the same sky, the same misery with no end in sight on any model. What they are experiencing has a name. It is called atmospheric blocking, and it is one of the most destructive and least understood weather phenomena on Earth. It has caused famines, collapsed harvests, broken heat records that stood for a century, and killed tens of thousands of people in single events. And the evidence that it is becoming more frequent, more intense, and more persistent as the planet warms is one of the most alarming findings in all of modern climate science. The worst weather pattern of the summer is not a storm that is coming. It is a stillness. And it may already be building above your head right now. To understand atmospheric blocking, you first need to understand the system it disrupts, because the disruption only makes sense against the background of how the atmosphere normally moves. The mid-latitude atmosphere, the band of the planet between roughly 30 and 60 degrees latitude, where most of Europe, North America, and large parts of Asia sit, is dominated by the westerlies. These are the prevailing winds that blow from west to east, driven by the rotation of the Earth and by the temperature difference between the warm tropics to the south and the cold polar regions to the north. The westerlies are not just surface winds. They represent a deep layer atmospheric flow that organizes itself into the jet stream, that fast-moving river of air at high altitude that we have discussed in other contexts. The jet stream is the train track on which weather systems travel. Low-pressure systems, with their clouds and precipitation, and high-pressure systems, with their clear skies and stable conditions, are steered by the jet stream. In a normal, healthy westerly flow, those systems move efficiently from west to east, spending a few days over any given location before moving on. Weather changes, seasons progress. The atmosphere breathes. Blocking occurs when this orderly westerly flow breaks down. Instead of flowing smoothly from west to east, the jet stream develops a large amplified ridge, a northward bulge, that becomes detached from the main flow and persists in place. This detached ridge is the blocking high. It is a massive dome of high pressure that sits fixed in the atmosphere, often 5 to 10 kilometers above the surface, deflecting the normal westerly flow around it rather than allowing it to pass through. Weather systems that would normally be steered through the blocked region by the jet stream are instead pushed to the north or south, leaving the region beneath the block cut off from the normal progression of weather. Meteorologists call this a Rex block or an omega block, depending on the specific pattern. The omega block gets its name because the shape of the jet stream flow around the blocking high looks like the Greek letter omega, but the essential mechanism is the same. A fixed, stationary high-pressure system that refuses to move, deflecting everything that tries to dislodge it, maintaining the same conditions beneath it day after day until the block finally collapses. The conditions beneath a summer blocking high are the conditions of a heat wave of the most extreme kind. High pressure causes air to sink, and sinking air compresses and warms. The sky is clear because sinking air suppresses cloud formation. The full intensity of summer solar radiation beats down on the surface without interruption, day after day. And because the block prevents weather systems from moving through, there is no cool front, no cloudy period, no rainy day to interrupt the accumulation of heat. Temperatures rise not just to the levels typical of a hot summer day, but continue climbing above those levels day after day as the blocked pattern persists. The energy input from continuous sunshine accumulates in the land surface, in the vegetation, in the buildings and roads of cities, and in the atmosphere itself, building temperatures to levels that can shatter records that have stood for a century or more. The Russian heat wave of 2010 is the defining modern case study of what an atmospheric blocking event can do to a country caught beneath it. In the summer of 2010, a massive blocking high established itself over western Russia and refused to move for approximately 50 days. 50 days. For nearly 2 months, the same anomalous high-pressure pattern sat over one of the largest countries on Earth, delivering temperatures that Moscow had never recorded in its entire meteorological history. Moscow hit 38, 2 degrees Celsius on July the 29th, 2010, shattering the previous all-time record of 36. 8 degrees set in 1936. The heat was not confined to Moscow. Across western Russia, temperatures ran 10 to 15 degrees Celsius above normal for week after week. Wildfires broke out across the drought-parched landscape and burned out of control for months, blanketing Moscow and surrounding cities in dense, acrid smoke that drove air quality to levels hazardous even for healthy adults and life-threatening for anyone with respiratory or cardiovascular conditions. The combination of extreme heat and extreme smoke created a public health catastrophe of staggering proportions. The human death toll from the Russian blocking event has been estimated at approximately 55,000 excess deaths, a figure derived by comparing actual mortality during the heat wave period to the expected mortality based on historical patterns for that time of year. 55,000 people. That is a death toll comparable to a major war, delivered by weather. The agricultural losses were equally catastrophic. Russia's wheat harvest in 2010 was approximately 40% below expectations. The Russian government responded by banning wheat exports, a decision that contributed to food price spikes in the global wheat market that reverberated through food importing countries and contributed to the social instability that preceded the Arab Spring uprisings of 2011. A single atmospheric blocking event over Russia, lasting 50 days, helped set the stage for political upheaval across North Africa and the Middle East. That is the reach of what happens when the atmosphere stops moving. The 2010 Russian block was extreme but not unique in the historical record. Atmospheric blocking events have been documented throughout the instrumental weather record and show up in paleoclimate proxies going back centuries. The European heat wave of 2003 that killed approximately 75,000 people was also driven by a blocking pattern, a persistent high-pressure system over Western Europe that prevented the normal summer weather progression for 2 weeks in August. The Australian heat waves of 2009 and 2019 that preceded catastrophic bushfire seasons were associated with blocking patterns in the southern hemisphere. The North American drought of 2012 that reduced corn yields by 13% was maintained by a blocking pattern in the jet stream over the continent. Blocking is not an exotic or unusual meteorological occurrence. It is a recurring feature of the mid-latitude atmosphere that, when it occurs in the wrong place at the wrong time, can be catastrophic for the human systems living beneath it. What makes atmospheric blocking particularly treacherous from a forecasting perspective is that numerical weather models, the computer simulations that produce the forecasts you see on weather apps and television, have historically struggled to predict blocking events accurately beyond about a week in advance. The chaotic, nonlinear dynamics of the atmosphere make extended-range forecasting difficult in general, but blocking events have proven especially challenging because they involve the large-scale reorganization of atmospheric flow patterns that models tend to underpredict in both frequency and persistence. A model might correctly predict that blocking conditions are likely to develop over a region in the coming week, but then underestimate how long the block will persist, predicting 3 or 4 days of anomalous heat when the actual event delivers 3 or 4 weeks. This forecasting limitation has direct consequences for emergency management, agriculture, water resource management, and public health preparation. When you don't know a blocking event is coming until it is already underway, and when you can't reliably predict how long it will last once it starts, the window for effective preparation collapses. Forecasting centers have made genuine progress on extended-range blocking prediction in recent years. The European Center for Medium-Range Weather Forecasts, ECMWF, which operates what is widely regarded as the world's best global weather prediction system, has invested heavily in improving extended-range prediction of large-scale flow patterns, including blocking. The development of ensemble forecasting systems, which run many slightly different versions of the atmospheric model simultaneously to capture the range of possible outcomes, has improved this probabilistic prediction of blocking onset. But the fundamental limits of atmospheric predictability mean that the 2 to 4 week warning lead times that would allow meaningful preparation for a major blocking event remain difficult to achieve reliably. Agricultural systems, water managers, energy grid operators, and public health agencies are often still reacting to blocking events rather than preparing for them. The agricultural consequences of blocking deserve their own careful examination because they operate through multiple pathways simultaneously, and because the cumulative impact of more frequent blocking events on global food security represents one of the most significant but least publicly recognized risks in the entire climate and weather space. When a blocking high parks over a major agricultural region in summer, the consequences are not limited to the direct heat stress on crops, though that alone can be devastating. Drought develops rapidly under the clear skies and warm temperatures of a blocked pattern as evapotranspiration, the combination of evaporation from soil and transpiration from plant leaves, draws moisture out of the soil at rates that precipitation cannot replace when the block prevents the normal westerly weather systems from bringing rain. Soil moisture deficits that would normally take months to develop can open up within weeks under an intense blocking pattern. Rivers and reservoirs fed by precipitation across the blocked region drop. Irrigation demand spikes precisely when surface water availability is declining. Groundwater is drawn down to compensate, accelerating the depletion of aquifers that, in many agricultural regions, are already under long-term stress from over-extraction. The 2012 North American drought demonstrated this cascade with painful clarity. The blocking pattern that maintained dry, hot conditions over the Corn Belt for much of the summer drove what the United States Drought Monitor classified as the most extensive drought in the contiguous United States since the 1950s. Roughly 60% of the lower 48 states experienced drought conditions at the peak. The corn crop, the United States is the world's largest corn producer, suffered a yield decline of approximately 13% from the previous year, contributing to a surge in global corn prices that affected livestock producers, food manufacturers, and consumers worldwide. The soybean crop was similarly stressed. Insurance claims from crop losses exceeded $10 billion in the United States alone. Rural communities across the agricultural heartland experienced economic contractions that took years to recover from. And the blocking pattern that caused all of this was, by the standards of what climate models project for the future, relatively short-lived and moderate in its intensity compared to what a warmer atmosphere may produce. Blocking events do not only deliver heat and drought. Depending on where the blocking high is positioned and what it deflects around its edges, the same event that delivers prolonged heat to one region can simultaneously deliver prolonged wet conditions to another. The ridge deflects the jet stream and its associated weather systems to the north or south of the block, concentrating those systems in the areas immediately adjacent to the blocked region. During the 2010 Russian block, Pakistan experienced catastrophic flooding. At the same time, Moscow was setting heat records. The same atmospheric pattern that was deflecting weather systems away from Russia was funneling an unusual concentration of moisture-laden systems into the Pakistan region, ultimately delivering what was described as the worst flooding in Pakistani history, affecting approximately 20 million people and killing close to 2,000. The block over Russia and the floods in Pakistan were not coincidentally simultaneous. They were two expressions of the same distorted atmospheric circulation. This simultaneous, opposite extreme signature of blocking events, heat and drought on one side, floods on the other, creates a compound impact on global food systems that is more serious than either extreme alone. When the same atmospheric pattern that destroys a wheat crop in Russia also destroys a rice crop in Pakistan through flooding, the combined impact on global food, commodity markets, and food security in import-dependent countries is multiplicative. Food systems have some resilience to localized failures. A bad harvest in one region can be partially compensated by imports from regions that had good harvests. But when a single atmospheric blocking pattern simultaneously damages major producers on both sides of it, the compensating mechanism weakens. Prices rise globally. Import-dependent countries, particularly lower-income ones, face food security stress. Populations that spend large fractions of their income on food, which describes much of the developing world, face genuine hardship. The human consequences of atmospheric blocking therefore extend far beyond the people living beneath the block itself, traveling through commodity markets and supply chains to reach populations on the other side of the world who may not even know what atmospheric blocking is. Now let's address the question that has become increasingly urgent in climate science. Is atmospheric blocking becoming more frequent, more persistent, or more intense as the planet warms? The answer, based on the current state of research, is complicated and actively debated, but the weight of evidence points in a direction that should concern anyone thinking carefully about future weather risk. The mechanism most commonly invoked connects back to Arctic amplification, the disproportionately fast warming of the Arctic region that is shrinking the temperature gradient between the poles and the tropics and weakening and destabilizing the jet stream. A weakened, more meandering jet stream is more prone to developing the amplified ridges and troughs that can detach and persist as blocking patterns. Several research groups analyzing the observational record have found increases in blocking frequency and persistence in the Northern Hemisphere over recent decades, particularly in summer, that are consistent with the Arctic amplification hypothesis. Other researchers, using different analytical methods and different definitions of what constitutes a blocking event, have found less clear trends in the observational data, and some climate model analyses suggest that future warming could actually decrease blocking frequency in some regions while increasing it in others through mechanisms that are still being worked out. The scientific debate is genuine and the uncertainties are real, but one thing that is not in debate is the consequence of the same blocking events occurring in a warmer background climate. Even if blocking frequency does not change at all, the baseline temperatures of a warmer world mean that when blocking does occur, the heat beneath the block starts from a higher point and reaches higher peaks. A blocking event that would have produced temperatures 10 degrees above the historical average in the climate of 1980 produces temperatures 10 degrees above the, now higher, average of 2024. The absolute temperatures reached are higher. The physiological stress on people and crops is greater. The wildfire conditions are more extreme. The drought develops more rapidly because warmer temperatures drive faster evaporation. Blocking events in a warmer world are more damaging for the same reason that the same injury is more serious when the body's baseline health is already compromised. The practical implications for how individuals, communities, and governments should think about and prepare for atmospheric blocking are significant and largely not reflected in current planning frameworks. Heat action plans in most countries are designed around the assumption that heat waves last days to perhaps a week or two, long enough to open cooling centers, check on vulnerable residents, and get through before conditions return to normal. A blocking event that delivers 3, 4, or 6 weeks of extreme heat demands a fundamentally different response. Cooling centers that run for a few days are manageable. Cooling centers that need to operate continuously for 6 weeks require sustained staffing, sustained energy supply, sustained logistics. Agricultural emergency responses designed around short-term droughts need to be reconsidered for droughts that develop within weeks and persist for months. Water resource management plans built around historical summer weather patterns need to account for the possibility that the normal summer weather pattern simply does not occur in a blocking year. Energy grids designed to handle peak summer cooling loads for a few days at a time need to be assessed against the possibility of those peak loads persisting for weeks. The summer that is building right now may or may not produce a major blocking event over your region. Atmospheric blocking is inherently difficult to predict far in advance, and the specific location and timing of blocking events cannot be reliably specified weeks ahead of time. But the climatology is clear. Blocking events happen every summer somewhere in the mid-latitudes. They have been among the most catastrophic weather events of the past 2 decades wherever they have occurred. And the combination of a potentially more blocking-prone jet stream and a warmer background climate means that the damage they deliver when they do occur is greater than it has ever been in the observational record. The worst weather pattern of the summer is not the dramatic one. It is not the hurricane with its visible fury, or the tornado that announces itself with a roar, or the flash flood that arrives in a wall of water. It is the stillness, the day after day of the same oppressive heat, the forecast that shows no change, no relief, no end, the atmosphere that has simply stopped moving and settled its full weight onto the land and the people beneath it. That stillness is atmospheric blocking. It has killed more people and destroyed more harvests and destabilized more governments than almost any other weather phenomenon in modern history. And it is coming, not as a possibility to be considered, but as a certainty to be prepared for. Because in a warming world with a destabilized jet stream, it is no longer a question of whether a major blocking event will occur over a populated region this summer. It is only a question of where, and for how long, and whether the people beneath it will have been told what they were facing before it was too late to do anything about it. The atmosphere is building towards something. When it stops moving, everything beneath it will feel the full weight of what that means. The question is not whether you are ready for the next storm. The question is whether you are ready for the weather to simply stop.